Hey, welcome back. This is JB Free, and today we are going to be talking about motion in two dimensions and projectiles, which I hope will make you smile, at least for a little while. Hey, we're going to give it a trial, see what happens. So, to start off, we must discuss the concept of engineering vector notation. This is primarily used by the C kids, but it is very valuable for even the AP 1 and 2 kids. It's also called unit vector notation. And in this type of notation, the symbol I hat, it's actually an I with a little hat on it. It represents a vector of magnitude 1 pointing in the horizontal direction. Whereas J hat, little hat over it, represents a vector of magnitude 1 pointing in the vertical direction. What this means is this. If you have something like 3I hat, okay, so let's say here's I hat right here. If this is I hat, it's length 1 right there. 3I hat would just be 3 times that thing. So 1 of those, 2 of those, 3 of those. That would be 3I hat. It's just a way of saying a vector that is 3 units in the horizontal direction. Another example might be this. 4j. 4j is a vector of magnitude blank in the blank direction. What would you say there? 4j, vector of magnitude 4 units in the vertical direction. Makes perfect sense. Now, this means if we extend this, when we're adding 3I hat and 4j hat, we're not just adding 3 and 4. The answer is not 7. We are adding 2 vectors, 3I hat and 4j hat. So this would be something like this. Here's our 3I hat vector that we had before. And then we add to that 4j hat, which is something like that. 4j hat. When we add those 2 vectors, that means we've got to add them vectorially. So here is our resultant vector right there. Now, if this is in meters, and this is in meters, this is 3I hat meters, and this is 4I hat meter, 4j hat meters rather. What is the displacement? Well, if you know your triangles, 3, 4, 5, this is going to be 5 meters. Now, it's not I hat or j hat. This is just the magnitude. It's length 5 meters. And what direction is that in? In other words, what is that angle right there? Well, if we do a little trigonometry, we can figure out that, well, if you got an angle that's got opposite side of 4 and a adjacent side of 3, that is going to be an angle of approximately 53 degrees above the horizontal. So we can express all vectors in terms of their I hat and j hat components. It's just another way of expressing components. Now the secret to projectile motion, and truly the secret to all vector problems, is as follows. All you got to do is resolve all vectors into their horizontal and vertical components. And you got to keep them, once you've separated them, keep them completely separate. Do not mix them ever. That is the most common mistake. You must keep them completely separate at all times until at the very last moment you can put them back together to find the magnitude and direction. So let's discuss some alternate methods for separating x and y, dealing with a vector situation here. Let's start with unit vector notation. In either method that you're going to use, you still have to separate this vector into its components. What we have right here is a vector that is a velocity of 40 meters per second, and it's directed at 30 degrees above the horizontal. So this is just the initial velocity. This doesn't show the path of the particle, which of course would be parabolic if we were talking about projectile motion. But this just shows the initial velocity. So we need to find the components of this. First, I'm going to find the x component, which goes out to there. So this is going to be v naught. So v x naught will equal v naught vector times the cosine of the angle theta. In this situation, that gives us 40 meters per second times the cosine of 30 degrees. And when you calculate that all out, this is 0.866. You get about 34.6 meters per second. So if you're going initially at 40 meters per second at angle 30 degrees, horizontally, initially, you're going at 34.6 meters per second in the horizontal direction. Now, let's figure out the vertical component of that. Here's the vertical component of that. And this is going to be Vy naught, and that'll be equal to V naught times sine of theta, or 40 meters per second times sine of 30, which I happen to know that's 1/2. So this gives me 20 meters per second. So this is how you can separate the components, but how do we express this now that we have the components? Well, if you want to express it in unit vector notation, you'd have to say something like this. V naught vector is equal to 34.6 I hat plus 20 j hat. I'm going to put this in parentheses and then put the units out here. So this completely describes that vector right there. Let's take a look at the alternate method for separating x and y, which is to make two separate columns. And of course, we'll put x on one side and we'll put y on the other side. So our x value to start off with, we already have done all the math here. This is going to be our x component, which we've already figured out is 34.6 meters per second. And our y component, right here, we've already also figured that out, is 20 meters per second. Now what I'm going to do is I'm going to handle this just like if I was doing a projectile motion problem. So what we've got is an object starts on the ground. Its initial velocity, this is not the, it is important to understand that we are not looking at the path of the particle. This is just the initial velocity. The path of the particle would be something like that, but we're not going to actually show that. We're just showing the initial velocity. But if I was going to do this as a problem to find out, let's say, where this thing's going to land, here's how I would do it. I would start off with figuring out my givens. In the x direction, I've already got this. I've got Vx initial is 34.6 meters per second. And because I also know that the acceleration in the x direction, notice there's not any initial or final in a situation of constant acceleration. I can just put ax, but note that ax for projectile motion problems is 0. There is no acceleration in the x direction, which immediately tells us, if we need to know, that that means that Vx final is also 34.6 meters per second. And it also means that if you needed to, you could find V bar, or the average velocity in the x direction, is also 34.6 meters per second. Now, I'm just going to define this point right here where we start as, let's just say, x naught. We're just going to define that as 0. I'll just say that's 0 right there. So our question might be something like, what is x final? What is x final? We don't know how much time it's going to be in the air, so we also need to know what the time in the air is. But generally, you can't find that from the x direction in this kind of a problem. So I have to go over the y direction. For my y direction, I've got 20 meters per second, so I have Vy initial is 20 meters per second. And we're going to assume that this is a symmetrical motion where it comes back down. So I know that the acceleration in the y direction is going to be 9.8 meters per second squared. Now there's something wrong with that. What did I do wrong? See if you can figure that out. Well, the problem is if I'm defining up as positive, that's the positive direction, the acceleration isn't positive, it's negative. So I've got to include that. My v final y, you may say, okay, vy final, if it ends up at the same height it started at right there, then my vy final is going to be the opposite of that, negative 20 meters per second. You can say that y initial is 0. We can just say it's starting at 0 height, starting on the ground right over here, 0 meters. Also, if it's a symmetrical situation, we might also be able to say that y final is 0 meters. So now the question would be, what would time be? Now the thing is, for time, I've got my initial and final velocities, I've got the acceleration. Well, I'm going to use the definition of acceleration because A is equal to v final minus v initial over time. We can solve that and then find that time is equal to v final minus v initial over the acceleration. And it's going to be critical that we have the right signs. This is a negative value here. This will be a positive value here. It'll be a big negative number, but it's over negative acceleration. I'll have a positive time. And then this value is going to just be able to go right over there and plug in for that. At which point we could find the horizontal displacement just by multiplying v bar times whatever time we got right there. That'll end this video for now, and we'll come back next time and do an actual AP Physics level problem. See you then.